Hello everyone, this is Siavash Ibrahimia. This is a PowerPoint presentation for class of Advanced Heat Transfer. The topic that I'm talking about is the heat and mass transfer during a sudden loss of vacuum in a liquid helium cooled tube. The part 2, the theoretical modeling. In introduction, this project is a theoretical model for nitrogen gas to propagate in a helium-cooled vacuum tube. The purpose of this project is to understand the gas dynamics and condensation in long tube systems, such as the partial accelerators, and design the safety operation to minimize the possible damage due to the vacuum loss. The pure nitrogen gas in a straight tube immersed in either normal liquid helium or superfluid helium. Air into the beamline tube can be condensed on the cold tube inner surface by a liquid helium tube. In this experiment, an upgrade helical tube system with an insulated inlet section, and it could accurately control the gas inlet mass flow rates and the location of gas condensation starts. This presentation helps us to understand the complicating physical processes involved in beamline vacuum brake, which will benefit to design the safe operation of accelerator beamline of cryogenic system. In more information, this vacuum brake experiment, the room temperature of the nitrogen gas at the control inlet mass flow rate is allowed to flow into an evacuated tube. This is housed in a helium cryostat. The mass flow rate of the nitrogen gas at the inlet of the copper tube can be determined by monitoring the rate of the pressure drop in the nitrogen tank. It takes just 25 milliseconds to connect the nitrogen buffer to the tube system, and the nitrogen gas flow velocity is assumed to be at the local speed of sound. To solving the problems, we have conducted numerical simulation to solve the 1D gas dynamics equations in the radial heat transfer equations using a two-step first-order Gundolf-type finite difference method. In theoretical model, this design has a tube with the inner diameter, which is equal to the 25.4 millimeter, wall thickness is 1.25 millimeter, and the length is equal to 6.45 meter, and the lower tube section with the length of 5.88 meter is made of copper and is immersed in the liquid helium bath. The tube section above the liquid surface is made of stainless steel and is wrapped by a multi-layer insulation MLI blanket nitrogen together with a vacuum jacket. The upper stainless steel section also incorporates a heater with a temperature controller such that its temperature is always maintained at about 77 Kelvin. This product allows us to control the nitrogen gas condensation in the tube. Analytical formulation. In gas dynamics, the nitrogen gas is an ideal gas and described as state by the ideal gas equation of state pressure times the molar gas times the density of a gas times the ideal gas times the temperature of the gas. To describe the dynamical evolution of the nitrogen gas in the copper tube, we consider the conservation laws of nitrogen, mass, momentum, and energy. In the equations of the mass conservations, the formula to find out the mass deposition is this one. The MC is equal to the M naught times the C effectiveness, the rate of a mass collision on the wall per unit area for ideal gas. This is the equation for the mass collision, and effective efficient can be modeled as this equation, which is equal to 1 minus P over P times the alpha. Alpha is a sticking coefficient. Equilibrium pressure can be calculated as P is equal to the surface pressure times the square root of Tg over Ts. Ts is the surface temperature. For the momentum conservation, this equation is essentially the Navier-Stokes equation for compressible fluid with the added term to account for mass deposition effect. The right-hand side of the equation is for the momentum loss to the tube wall due to the mass deposition. For the energy conservation equations, the two terms on the right-hand side of the equations for the loss of energy due to the nitrogen mass deposition on the tube wall and the convective heat transfer from the gas to the cold of the solid nitrogen frost layer. The Nusselt number equation that we see here for the nitrogen gas convective heat transfer is evaluated using the Cedar-Tate correlation. For the radial heat transfer, the position heat flux for the nitrogen gas to the frost layer consists of a contribution from both the energy associated with the deposition molecules, such as the kinetic energy, the sensible heat, and latent heat, and the convective heat transfer. The equation is here that we see here. Heat flux into the copper wall is the equation which is provided on this page. And the temperature differences to the heat transfer becomes an order of magnitude greater than that in nuclear boiling. For the steady film boiling regime, the widely accepted Breen-West water correlation is used in our simulation, where BW is a constant that slightly depends on surface. Analytical model, in order to solve the above mentioned 1D equation for the gas dynamics, we need to analyze the radial heat transfer and determine the frost layer surface temperature. The figure 2 shows a schematic of the relevant radial heat transfer processor, which is provided in this page. This is the analytical model of the advanced of the heat and mass transfer project. And for the data presentation and experimental graphs, this is a graph. The figure number 3 is comparing with the experimental observations. We first calculated the wall temperature curves at different locations along the tube as shown in figure 3. In figure 4, we are seeing more clearing the agreement between the simulated and the observed of the nitrogen gas propagation. We show in figure 4 both the major wall temperature curves and the calculated ones at the same thermometer location. It is clear that these two sets of curves match fairly well except at the last thermometer location. The last graph, which is the result graph, we see the we now discuss the dynamical propagation of the nitrogen gas in the tube. In figure number 5, we show the simulated spatial profiles of the nitrogen gas density, temperature, pressure, velocity, and the wall temperature in the tube at the number of propagation times. This profile shows 3 distinct regions. The first one is the inlet region. The inlet region is the gas pressure and density in this section are not constant, and they slowly decrease with the time due to the drop of a buffer bank pressure during the discharge of a nitrogen. The second one is a mass deposition region for a given propagation time, the region between the condensation starting point that the X is around 0.57 meter. And the third one is the tail region. This region refers to the tube section beyond the mass deposition region and is featured by very low gas pressure and density. Indeed, if one looks closely in the far tail part of the nitrogen gas property profile curves, there exists a shock front across which there is an abrupt change of the nitrogen gas properties. And at the end, in the conclusion, the experiment is presented a theoretical model that systematically accounts for the propagation and condensation of nitrogen gas in an evacuated helium number 1 cooled tube. Our simulation results provide some important insight into the complex heat and mass transfer process of the vacuum break in the cold tube. The first one is the apparent gas from the propagation observed in the experiment indeed corresponds to the propagation of the from mass deposition region. The mass deposition region, the gas deposition occurs predominantly in the steady deposition subregion with a nearly time-independent mass deposition rate. And eventually, this experiment is also conduct simulation for gas propagation in the helium number 2 cooled tube. These studies are produce key knowledge for the development of safety standard for beamline cryogenic system design. And at the end, I'd like to say thank you, everyone. Thank you for your watching.